Welcome back to this series on architectural simplification. Today we'll be looking at the impacts of including a cache in your architecture for the purposes of Reid performance. In today's demo, the before scenario will look like this. I'll have a service that writes to a relational database and to a cache. I'm going to simulate reads and writes to this environment, but let's say for the sake of argument that in this scenario, a cache has been included because of a perceived need. The after scenario involves a service writing to a relational database that this time can scale for both reads and writes. A user therefore makes all of their requests against that database without the need for a cache. The compose file for both the before and after scenario is the same. I spin up a 3-node Cockroach DB cluster with an HA proxy in front of it, and I also spin up Redis for the before architecture. The before code looks like this. I load products from an ids.json file, which I'll show you in a minute. I connect to the cache. I connect to the database, I expose an endpoint that allows customers to get stock for a particular product ID, and then I simulate writes. This is important because it will simulate what happens in a read-write balanced environment where writes to the database will invalidate the cache. In the handle product endpoint, I take the ID from the path and I use that to fetch a value from the cache. If it doesn't exist, I read it from the database and then write the value into the cache. I'm not simulating any kind of failures in this scenario, it's all happy path testing. In my writer, I simulate at a given interval a write to the database and a cache invalidation. The after code is quite a lot simpler than the before code, 118 lines of code versus 157 lines of code. I load the products from the ids.json file, I connect to the database, I expose the same endpoint, and I start my writer. The only difference here is that I don't have a cache in front of the database. Let's spin up the infrastructure for the before and after scenarios now. I'll spin up Cockroach DB, I'll initialize it and I'll connect to it. Next, I'll create a table called stock that has a product ID and a quantity, and I'll insert 100 rows into that. Next, I'll select all of the data out of the stock table and build a JSON object that I'll store in a file called ids.json. Now we're ready to run our before scenario, our cached server. I'll run 3 examples, the first of which I'll be writing to the database every 100 milliseconds, and I'll run a load test against that. I'll return the average and the P99 latency. I'll now increase the write throughput to every 50 milliseconds and run the same load test again. And finally, I'll increase the write throughput to every 10 milliseconds and I'll run the load test again. I'll now run the after scenario, the server without caching, writing to the database every 100 milliseconds. I'll run a load test. I'll now increase the write throughput to every 50 milliseconds and run another load test. And finally, I'll increase the writes to occur every 10 milliseconds and run one final load test. Let's look at what we're seeing in those results. These 6 lines correspond to the 6 tests that we've just run. Up here, we see the before scenario with caching, and down here, we see the after scenario without caching. What we were seeing when writes were made to the database every 100 milliseconds, 50 milliseconds, and 10 milliseconds for the caching example, the value of the cache decreases. And that's more or less what we're seeing. When we were making 10 writes per second, we saw a P99 latency of 12.5 milliseconds. When we increased that to 20 requests per second, that dropped ever so slightly to 12.9 milliseconds P99 latency. And when we were making 100 requests per second, that increased to 20.5 milliseconds. These aren't huge numbers, but it does indicate a slight pattern. When we run our tests at intervals of 100 milliseconds, 50 milliseconds, and 20 milliseconds, there is also a trend to be seen, and that's likely because of database contention, where we're writing to rows that we're trying to read from, and the locking involved there. But what's interesting is there isn't a huge difference between these values. The 99th percentile latencies are quite similar between the cached example and the non-cached example. In all of the tests I was running, I aimed for a constant rate of 2,500 requests per second, and I achieved that on all 6 of the test runs. So in summary to all of this, there's a negative correlation between write throughput and cache payoff. As your writes increase in frequency, the value of your cache decreases, because when you're trying to make a read against the cache, that value may have already been invalidated. Caching can, of course, improve performance. There are different levels of caching that you can perform. There's in-memory caching, which is sometimes referred to as level 1, which happens within a session. And then there's level 2 caching, which might be an external cache. Redis is sometimes used for this, Hazelcast is sometimes used for this, etc. In a second level cache, your cache writes need to make a network hop. You make a network hop to the cache to see if the value exists, and if it doesn't, you make a second network hop to the database to fetch that value, before making a third hop back to the cache to set the new value. In any scenario where caching is used, be that first level or second level, you're losing the ACID guarantees that the database provides. So caching isn't appropriate for all types of data. Time-sensitive data, transactional data, security-sensitive data, or just data that's not very long-lived don't make great candidates for caching. What I hope to have demonstrated in this example is you don't always need a cache for read-heavy environments. And in any environment where you're caching, that will necessitate additional application complexity. You can use local in-memory caching per microservice, but then that adds the further complexity of how do you synchronize multiple services, each with potentially a different in-memory representation of that data. And finally, only consider caching after you've performed load testing yourself on your own systems. Your environment and its read-write characteristics will dictate your need for caching.